This is Algebra 2, Unit 12, Lesson 3, Normal Bell Curves and Finding Z-Scores. We have to review a little bit first for this, just a few terms, and then we're going to get right into the normal bell curve. If you ever hear that the data has been normally distributed, what they're talking about is something called a normal bell curve. And a real good example of this would be like test scores, or if in your family maybe you have a baby and the doctor says the baby is in the 50th percentile or the 70th percentile for a certain thing. They're talking about a bell curve. Essentially 100% of the data can fit under a bell curve. And well, technically they say 99.7% of the data can fit under a bell curve. And then that leaves the 0.3% to be your outliers, things that just can't be put into the normal set of data without skewing it a bit. So the bell curve is probably the best organization that we have to get a really simple understanding of where you fall within that data. So if somebody says that, a baby is in the 70th percentile for height, that means they're taller than 70% of other babies their same age. Or if they say they are in the 20th percentile for weight, that means 20% of the babies out there would weigh less than they do for their age. So it's a really good way of doing a really quick estimation of where somebody stands in the whole realm of data. Another good one would be like SAT scores or any kind of standardized test scores. If they say you're in the 75th percentile, that means you scored higher than 75% of the population. And it's going to be really easy to tell where the majority of the data lies because of the shape of the bell curve. And so that's what we're getting to. First of all, you need to understand that a mean is the same thing now as it was back in elementary and middle school. The mean is the average of all the data. So if you add up all the numbers in the data and divide by the number of numbers you have, you will get the mean. So when we talk about the mean on the normal bell curve, that is what we're talking about. And the mean on a normal bell curve will have a z-score of 0. That's where the middle ground is. That's where the very center of the data would lie. Okay, so that's your mean. A standard deviation is something that's very important when we're talking about bell curves. Standard deviation is how spread apart the data is. So like it's how far the data lies from the mean. So if you have a large standard deviation, a very large number, that means the data is very spread out. If you have a very small standard deviation, that means the data was pretty close together. And so knowing what the standard deviation is can give you a better understanding of your numbers. And then the normal bell curve is a universal way to display data. And the good thing about this is all data, no matter what it is, can be put into a normal bell curve with a specific, like with its own standard deviation. So no matter how spread out or how close together the data is, we can do a bell curve to signify where that data would lie. So here are just some generic bar graphs to let you see some basic data. And you can see here, and this a lot of the data spreading out more toward the left here, and it seems like the majority of the numbers are toward the right. And on this side, the majority of these numbers are toward the left, and it's more spread out as you move right. Or your bar graph can jump all over the place right here. And so it's really hard to interpret the data. You wouldn't be able to tell where 50% of the data lies by looking at a bar graph. So it makes it a little bit confusing. It's even hard to tell where this data is split in half, to the higher half and the lower half. I mean, it's just really hard to tell where that would be. But if we take it and put it in as a bell curve, it just kind of shows how the bars would lie out within a bell curve if you had it in the shape of your normal distribution curve. So it's called a bell curve because the shape sort of looks like a bell. So here is a basic shape for the bell curve. Understand that most of the data would lie in the thicker part of the bell curve, and then very few parts of the data would be over in this area. And so the first thing that we need to talk about is the empirical rule when it comes to dealing with the normal bell curve. Now, understand this line right here will represent your mean value. And your mean value is, again, the average of all the numbers. So I've got the mean labeled right here. And then with a bell curve, you need to understand 50% of the data is going to be on this side of the mean, and the other 50% of the data is going to be on this side of the mean. The upper end of the data would be on the right, the lower end of the data will be on the left. Now, the good news is we don't have to worry about outliers. We're going to talk about everything being pretty much 100% underneath the bell curve. And so what we need to talk about is how these things will be labeled. So, as I said before, our mean goes right here. So let's just suppose we have some data, and I'm going to give you some just random numbers for the mean and the standard deviation so that you can see how we would label a bell curve. So if I had a mean, and this is the symbol for mean, it's a mu, Greek letter. That is the symbol you will see in formulas for mean. So I'm going to say that the mean here is 52. And let's say the standard deviation for our data is 5. Now, this symbol right here is the standard deviation symbol. I guess you could say it's kind of a sideways 9. It is also a Greek letter. And we're going to use a formula for z-score later that uses these two symbols. So it's important that you do know what those two symbols are. All right, so in the bell curve, to label this bell curve, my mean is going to be right here. That is my middle number. So I'm just going to label my mean with 52. So I've got my mean labeled. And then each of these lines, and you're only going to see 3 lines to the right and to the left of the mean, because most of the data, 99.7% of the data, can lie within these 3 lines of the standard bell curve. And the labels that we put here, 1 standard deviation to the right of the mean would be here, 2 standard deviations to the right of the mean would be here, 3 standard deviations to the right of the mean would be here. And so if my standard deviation is 5, then the number that goes here would be 52 plus 5, or 57. So you can see here, I have labeled the right-hand side of my normal bell curve. To the left of the mean, 1 standard deviation to the left is here, 2 standard deviations to the left is here, 3 standard deviations to the left is here. So what I would do to get this number is subtract the standard deviation from the mean. So 52 minus 5 would be 47. And here I have labeled the left-hand side. So the mean is 52. 1 standard deviation below the mean would be at a 47. 2 standard deviations below the mean would be at a 42. 3 standard deviations below the mean would be at a 37. Let's say these are weights of middle to large breed dogs. We could say how many standard deviations away from the mean would a dog that weighs 62 pounds be? Well, a dog that weighs 62 pounds is 2 standard deviations above the mean. A dog that weighs 47 pounds is 1 standard deviation below the mean. A dog that weighs 50 pounds would be in here somewhere, okay? We will eventually be able to find something called a z-score for where that lies, okay? Now, let me compare these things to the z-score so you know how z-scores will work. Your mean will always have a z-score of 0. So the mean z-score is always a 0. This is 1 standard deviation above the mean, so this would have a z-score of 1. This is 2 standard deviations away from the mean, to the right of the mean. This is 3 standard deviations to the right of the mean. So what do you think those would be? Hopefully you're saying this would be a 2 and this would be a 3. The z-scores for these 3 lines are going to be 1, 2, and 3. This is 1 standard deviation to the right of the mean, 2 standard deviations to the right of the mean, 3 standard deviations to the right of the mean. They are positive because we're moving toward the right. Remember, right motion toward the right is a positive. Well, let's move toward the left. What if we have the number 1 standard deviation below the mean? Well, that would have a z-score of a -1. So I've got the z-scores for the 3 standard deviations below the mean. This one is at a -1. This one is at -2. This one is at -3. So I could say something like this. I could say, if you have a dog that weighs 65 pounds, approximately how many standard deviations away from the mean would you expect it to be? Well, 65 pounds is in between 62 and 67. So we would expect it to be between 2 and 3 standard deviations from the mean. How about a dog that weighs 40 pounds? Well, a dog that weighs 40 pounds would be in here, so we would expect it to be 2 to 3 standard deviations below the mean. And we can eventually figure out exactly what the z-scores are by using the z-score formula. So this is how a z-score, these numbers down here, and the mean and standard deviations relate to each other in a normal bell curve. So the next thing we need to talk about is the empirical rule. And what you need to understand is what percent of the data lies within each of these different sections. Now, we've already talked about 99.7% of the data can lie within the normal bell curve. Okay, so we're going to say that this section out here and this section out here hold a very, very small number of the members of the data. So this right here is our mean. We know that 50% of the data lies to the right of the mean. We know that 50% of the data lies to the left. 68% of the data will lie within one standard deviation of the mean. It could be from one standard deviation to the left or one standard deviation to the right. So if I write that in, we see that this is 68% of the data. And then we know that another 13.5% of the data is between -1 and -2, and 13.5% of the data is between 1 and 2. So I've drawn in some of the numbers here. We know 68% of the data lies within one standard deviation of the mean, and this is the mean. So within one standard deviation of the mean, we have 68% of the data. Within two standard deviations of the mean, we have 95% of the data. Now, if we just separate these individual sections into what percentages they are, each of these from 0 to 1, -1, and from 0 to 1, each of those is 34% of the data. This one is 13.5% of the data, and this one is 13.5% of the data. So altogether, the 13.5 plus 34 plus 34 plus 13.5 is 95%. So 95% of the data will lie within two standard deviations of the mean in a standard bell curve. So what that means is we have about 5% left on either side. So we've got about 5% left here and 5% left here. Look at these. These are percentages, not sevens. Sometimes kids get confused and think I'm writing a 7 there. So we've got 5% of the data here, 5% of the data here. 99.7% of the data is within 3 standard deviations of the mean. So the empirical rule says that 99.7% of the data has to be within 3 standard deviations from the mean. So this little bit right here and this little bit right here only account for a very, very small percentage, a 0.3% of the data, and that's data that is I would consider it an outlier. It's very rare that you have something that large or that small within the set of data that you're talking about. So this is something called the empirical rule. So we're going to have to answer questions when they give us the mean about the empirical rule, like where would 95% of the data lie? Where would 68% of the data lie? And so forth. So that's what we're going to get into next. So I've just taken a few delta math examples so that we can look at the percentages within the standard bell curve. Let's just call him Bob. I have no idea how to pronounce that name. When Bob commutes to work, the amount of time it takes him to arrive is normally distributed with a mean of 21 minutes and a standard deviation of 4 minutes. Using the empirical rule, what percentage of his commute will be between 9 and 33 minutes? So to do something like this, I usually draw a little quick diagram of a standard bell curve and label it with their mean and their standard deviation, and then I can get a really good idea of what's going on. So that's what I'm going to do. So here I have labeled a very simple standard bell curve. I've got my mean 21 here, which would have a z-score of 0. Then my first standard deviation, I add 4 to 21, get 25. Add 4 to that, get 29. Add 4 to that to get 33. And these have the z-scores of 1, 2, and 3. I subtract 4 to get each of these. So I've got 17, 13, and 9, and these have a z-score of -1, -2, and -3. Using the empirical rule, what percentage of his commute will be between 9 and 33? Well, 9 is here, 33 is here. Didn't we say that within 3 standard deviations of the mean, we have 99.7% of the data? So 99.7% of the data would be the answer there. I would put that in Delta Math and they would count it right. In the next one, when Colton commutes to work, the amount of time it takes him to travel or to arrive is normally distributed with a mean of 41 minutes and a standard deviation of 3.5 minutes. Using the empirical rule, determine the interval that represents the middle 95% of his commute times. Okay, I'm going to just draw a quick standard bell curve and I'm going to put in my measurements. Answer to this one, if I label it, I've got the mean is 41, and then I'm adding 3.5 to get each of these numbers, subtracting 3.5 to get each of these numbers. And so 95% of my data, remember, lies between 2 standard deviations. And so that means my interval for 95% of the data will lie from 34 to 48. So 95% of the people have commute times that are between 34 and 48 minutes. In this one, in an all-boys school, the height of the student body are normally distributed with a mean of 71 inches and a standard deviation of 3.5 inches. Using the empirical rule, determine the interval of heights that represents the middle 68% of male heights. Okay, so if you think about what this looks like, your standard deviation bell curve looks like this. The mean is right here, which was 71. 68% of the data lies within 1 standard deviation from the mean. So we know 68% of the data lies in here. So all we have to do is subtract 3.5 from 71. That will be 67.5. And then if we add 3.5 to 71, we get 74.5. So 68% of the data lies between 67.5 inches to 74.5 inches. This takes us to the formula for finding z-scores. The formula for a z-score is z equals x minus mu over standard deviation. So we need to understand what all these variables stand for. Well, z is your z-score, so that's what that means. Z will be the actual z-score. The m we talked about earlier, that is the mean of the set of data. That is the symbol for standard deviation. And the x is just a number from the data. So that's a member of the data. So they have to give you 3 out of the 4 of these in order to be able to find what you're missing. So we're just going to do a couple examples of this. So the z is the z-score, x is a member of the data, mu is the mean, and this is the standard deviation. And they will give you the formula if you're taking the SOL. You will have the formula. That's no big deal. You don't have to memorize it. You will have to memorize the empirical rule. They won't give you that. But the z-score, they do give it to you. They might say a set of data for test scores is normally distributed, and this is the information that we have. The mean test score was 71. Standard deviation for the test scores was 5. One of the test score data sets or data members is an 80%, and they want you to find the z-score for that test score of an 80%. That's when we would use our formula. So we know z equals x minus m over standard deviation. We are trying to find the z-score, so they didn't give us that. X is the member of the set of data. That would be 80. M is the mean, so that's 71. And this is your standard deviation, which was 5. So 80 minus 71 would be 9. So that's 9 over 5. And z-scores, as you will learn as we move forward, need to be rounded to 2 decimal places every single time. So always, no matter what, you will always round your z-scores to 2 decimal places. 9 over 5 gives me a z-score of 1.8. And if we're saying that's to 2 decimal places, that would be 1.80. I'm going to show you how to use a table to find z-scores for any value within the data set, and we would have to round to 2 decimal places, and the z-score you would look up in the chart would be 1.80 for the 1.8. So here I've got 2 more problems that are similar, but we're finding different things. Before we found the z-score, now they're going to give us a z-score and ask us to find one of the other things within the formula. So for the first one, it says the z-score is 2.2, The mean is 18, the data point is 22, and they want us to find the standard deviation. So I'm going to use the formula. I know my z-score is 2.2. My data point was 22. My mean was 18. I don't know what the standard deviation is. I will multiply over the standard deviation, and that gives me a 4. And then I would divide 4 by 2.2. And that gives me 1.81 repeating. With standard deviation or any other term, now z-score has to be rounded to 2 decimal places, but for the rest of these, you'll just need to read the directions and see what they ask you to round them to, and that's what you would do. For this one, the z-score is 1.25, the standard deviation is 2, the data score is 83, find the mean. Go ahead and pause the video, see if you can get that one, and then I'll come back and give you the answer in a few minutes. So right here I have that one worked out. Z equals x minus m over standard deviation. The z-score was 1.25. The data set member was 83. We don't know the mean, and the standard deviation was 2. I multiplied the 2 over to get 2.5, and then I moved the mean over to make it positive and subtracted 83 by 2.5 and ended up with 80.5. So these aren't too bad. These are very simple. Just plug it into a formula to find the z-score or one of the other data members.